there's nothing there at the moment.
No, I think it's too cloudy,
Not even a
really.
hint.
Not at all.
Yeah. OK, what time do you make it now?
Just turned 6 minutes past.
Oh, well. Well, that was local noon. And we were going to measure the length of the shadow cast by the pole. In other words, we were going to do a rerun of Eratosthenes' experiment to find the circumference of the Earth here at the Bishop Walsh School in Sutton Coldfield. But as you can see, the sun hasn't obliged us. However, as this programme is essentially about experiments, about the ideas and assumptions and the difficulties, that's perhaps not such a bad thing, because that's often happens in experiments. Things don't work out the way you expect them to. And anyway, we were half expecting this to happen when we came up here, so we've made allowances. We've taken contingency plans. But let's go right back to the beginning of the story. Let's go back a couple of hours and see how it all started. First of all, the pole. We need to know its height, but we didn't know how much it was going to sink into the ground once it was up. So we used a white reference mark and measured upwards from that to the top of the pole.
It's 298 centimetres.
The next stage was to get the pole mounted and vertical. Sounds easy, but there was actually quite a bit of work involved. We reckoned a large spirit level would be good enough to enable us to get the pole sufficiently vertical, get it pointing directly away from the centre of the Earth. A bit of adjustment to the guy ropes. And not only must the pole be vertical, but the shadow must be cast along the horizontal, hence the base plate. Again, a bit of adjustment. And recheck. But we need to know the height of the pole above this base plate, and that meant measuring up to our white reference mark.
That's, quote 30.
So the 30 had to be added to the 288 to get the total height of the pole, 318 centimetres. Then we're all set to measure the shadow length.
Right.
And this is where our contingency plans came in. We decided to start marking the end of the shadow half an hour or so before local noon.
Can you see it?
Yeah. It's there.
There.
Yeah.
Okay.
Then, as the sun moved round in the sky, we marked the new position of the shadow. The shadow moved on, and we put in a third pin. Deciding exactly where to put the pins wasn't easy. The end of the shadow was pretty fuzzy.
Yeah. The sun's gone again.
And the sun was in and out all the time, so we stuck another pin in at every single opportunity. In this way, we'd hoped to build up a whole line of pins spanning noon. But the noon pin itself, well, you saw what happened. Great, great.
Yes. Fine.
So, although we're a bit unlucky over noon itself, we've managed to get some sort of line, and another quarter of an hour will see us get the full arc. So we've now got a whole arc of pins, and we know that noon was about halfway between these two here. So we can interpolate between those two and put in a pin about there. Yeah. And that now corresponds to the end of the shadow at noon. And you can see that that is more or less the shortest shadow length, because this board arc here is a circle of constant radius. So all we've got to do is measure the length of that shadow. If I take the far end of the tape. Okay.
Yeah.
Pull it tight. Yeah.
It's okay.
Yeah.
Well, I think That looks about 177, 178 centimetres.
Yeah, call it 178 centimetres.
Well, there's the two readings, and what my job is to analyse them. You remember the setup we had at Sutton Coldfield? We had a pole, and it was casting a shadow. Well, what we really want is the angle between the sun's rays and the local vertical. That's this angle here. Now call that theta s. Now, when you did this in the unit, it was quite easy because theta s was a small angle, and so we could make the small angle approximation. Remember, that applies for circles, where you have the angle theta s in radians is equal to the, in this case, the shadow length over the pole height. In the circle, it was the arc length over the radius. Now, we can't make quite the same approximation because our angle is small. What we have to do is a bit of trigonometry. Now, in a right-angled triangle, the tangent of the angle is equal to the opposite side over the adjacent side. That's the same ratio. So in this case, the tangent of theta s is equal to the opposite side, that's the shadow length, 178 centimetres, divided by the adjacent side, that's the pole height, 318 centimetres. Let's just work out what that is on the calculator. That's 178 divided by 318. That's equal to, oh, well, I'm not going to keep all those numbers, there's no point. If I cut them off at 3, then we've got the same number as we had in the measurement, so it's 0.560 rounding off. Okay, so the tangent of this angle is equal to 0.560, and the calculator can tell us what the angle's equal to. All I do is press inverse tangent, there's the answer, 29.2 degrees. Okay, well, that's the angle. And what I've got to do next is relate that angle to the size of the Earth. We've assumed that the light from the sun is parallel. And as you know, we did our experiment at Sutton Coldfield. Because the sun wasn't directly overhead at Sutton Coldfield, our vertical pole cast a shadow along the ground. And it was this that allowed us to deduce the angle between the sun's rays and the pole. That's the one I've just calculated. But this angle is equal to the angle at the centre of the Earth between the radius drawn to Sutton Coldfield and the radius to the point on the Earth where the sun is directly overhead. So the angle at the centre is also theta s. Well, so far, everything that I've done is exactly as Eratosthenes did it. Remember, he made his measurements at Alexandria, somewhere near the mouth of the Nile here. And he made his measurements about 2,000 years ago. So he wasn't quite as sure about directions or distances as we are today. But what he did know was that Syene, which was near enough due south of him, at Syene the sun was directly overhead on Midsummer's Day. That's the day he made his measurement. Now, we didn't make our measurement on Midsummer's Day. And so we don't know where our Syene is. We don't know where the sun was directly overhead. Now, that's not really a problem. All we have to do is find another location, which is on the same line of longitude, make sure we can do the measurements on the same day. And the place we've chosen to do it, well, here it is. It's Peterhead in Scotland. And you can see that near enough, Sutton Coldfield and Peterhead are exactly as far west of Greenwich as each other. Right. Now, how does that get us out of our problem? Peterhead is due north of Sutton Coldfield, and the experiment we need to do there is exactly the same as the experiment we did at Sutton Coldfield. A vertical pole, a shadow, and measure the angle. The angle will be different from that at Sutton Coldfield, but the argument's just the same. That is, the angle measured is equal to the angle at the centre of the Earth between the radius to P and the direction of the sun's rays. We'll call this angle theta P. Now, the difference between the two angles we've measured is just the small angle between the radii to the two places where we've measured them. So the angle theta P minus theta S is the angle at the centre corresponding to the arc PS. Well, I'm nearly there now. I've already got the angle theta S. That's the one we measured at Sutton Coldfield. What I need now is theta P. I've already got that. Here we are. Theta P is 34.4 degrees. Let's note that down. Theta P is equal to 34.4. So the small angle in the segment, that's theta P minus theta S, this angle here, is just equal to the difference in these two readings. And if I can manage to do that, theta P minus theta S is 5.2 degrees. So all we're left with now is the arc. What's the length of the arc PS? Well, I've measured it up on a map, measured the distance between Sutton Coldfield and Peterhead, and that comes to 552 kilometres. So, the angle of 5.2 degrees carries an arc of 552 kilometres. So the question we've got to ask is, what arc length is carried by an angle of 360 degrees all the way round? Because that angle will just be the circumference of the entire circle. That's the circumference of the Earth. Now, I'm going to leave you to do that, and it might be interesting for you to compare the result that we've managed to get with our measurements with the correct result, and see whether we're as accurate as we should have been, see if our errors are about right.
But we said right at the beginning of this programme that we were going to be talking about some of the assumptions lying behind the experiment. I don't know whether you noticed or not, but there has been an assumption running all the way through that Eratosthenes experiment at Sutton Coldfield, and that's that the light coming from the sun falling on the Earth could be assumed to be parallel rays. Now, why on earth did we feel justified in making that assumption? After all, a point source of light sends its rays out in all directions. But the further away from the source we are, the more parallel the rays reaching us become. Unfortunately, it's not quite as simple as that. The sun may be a long way away, but it's not a small point. It's a whole collection of radiating sources of light. You can get some idea of the difference this makes by considering the effect of the two extreme points, both radiating in just the same way as before. So if you're a long way away, there are parallel rays coming in from the top of the sun and parallel rays coming in from the bottom of the sun, but at a slightly different angle. If light only came from the top of the sun, and we put an object in the path of the light, it would leave a cylindrical shadow region. But there's also light coming from the bottom, leaving another shadow region. So the combined effect is to produce a tapering region which is perfectly dark, surrounded by a region of partial darkness. So you can see that this assumption about parallel rays of sunlight isn't quite correct. And that's why at Sutton Coldfield with the Eratosthenes experiment, we found that the shadow was just a little bit on the fuzzy side. But it didn't matter too much there. All it meant was that it was a bit more difficult to measure the length of the shadow. But that's not always the case. This parallel light approximation can get us into trouble. For instance, when you had the photograph of the lunar eclipse and you were asked to compare the diameter of the Earth with the diameter of the Moon, now there, the assumption can get you into real problems. And way back 2,000 years ago, Aristarchus realized that. and he had a fancy way out of it. It involved a bit of careful reasoning, but he said, look at the situation when you've got a solar eclipse, a situation like this, where the moon is between the Earth and the incoming sunlight. He said, what happens in this situation is we get a shadow cone, and this shadow cone tapers to a virtual point by the time it reaches the surface of the Earth. And we know that's the case because we know you can only see a total eclipse from a very small area of the Earth. Move outside this area and you don't see the total eclipse. And that's still true today, of course. To take photographs of a solar eclipse, we go off to the middle of the Sahara Desert or somewhere. So what Aristarchus was saying is that the cone narrows by 1 moon diameter over 1 moon's orbital radius. But this is the wrong setup. We aren't interested in the solar eclipse, we're interested in the lunar eclipse, and that happens when the moon is round the other side of the Earth. Now, here, of course, it's going to be the Earth that produces a shadow cone. But what Aristarchus said, quite cleverly, was, hey, look, this is the same distance. It's 1 moon's orbital radius. And if it's the same distance, it seems reasonable to assume that the narrowing is going to be by about the same amount, 1 moon diameter. So the shadow that you see cast on the moon by the Earth during a lunar eclipse is not going to be the same size as the diameter of the Earth, but it's going to be smaller by 1 moon diameter.
Now what I'm going to do is translate Keith's argument into mathematics, put it down in equations. What he said was that the diameter of the shadow is not equal to the diameter of the Earth. In fact, the diameter of the shadow is equal to the diameter of the Earth minus the diameter of the moon. Now, what you measured in the text was the ratio of the diameter of the shadow to the diameter of the moon. It's this quantity. And all this is the left-hand side of the equation that I've already written down divided by dm. So I can preserve this equation if I just divide the right-hand side by dm. So we have the quantity that you measured, ds over dm, is equal to dE over dm, and that's what we want in the end, minus dm over dm, and that's just 1. Okay, this ratio is what we want, and we can isolate that quite simply. All we need to do is add 1 onto both sides of the equation. Remember, we're doing the same thing to both sides again. So, if I add 1 onto the left-hand side, the quantity you measured plus 1 is equal to the quantity, the ratio that you want. And the 1's go out, minus 1 plus 1. Well, there we are, that's all there is to it. Couldn't be more simple. All you have to do is take the ratio that you calculated and add 1 onto it.
Better? Well, in case you're wondering, this is not my back garden. We've borrowed the patio here at the Science and Technology building at Walton Hall to do the next step in the experiment, which of course is to measure the distance to the moon by eclipsing it with your plastic disc. Now, I'm not actually going to do this experiment, that's your job, but I would like to draw your attention to 1 or 2 key points. First of all, as you can see, you don't need a perfect full moon in order to be able to do the experiment. As long as you can match the curvature of your disc with the curvature of that part of the circumference that is visible, you'll get some sort of result. And secondly, don't aim to get one precise eclipse distance. Aim to find the range of possible eclipse distances, because in that way, we'll be able to have some sort of idea of the confidence to place in your finally worked out distance to the moon. And when you do work out that distance to the moon, you'll find that you have to plug in the diameter of the moon to the formula. Now, when you do that, plug in the corrected value for the diameter, corrected in the way that Steve just explained to you. That's rather important. If you're at all hazy about that correction, have a look at the broadcast notes again after this programme. Now, I don't know whether you're feeling just a trifle disillusioned with the Science Foundation course so far. Thought you were signing up for a course on modern science, and here we are plying you with all this stuff about the ancient Greeks. But you see, the thing is that when you're working at the frontiers of science, as the Greeks were, you often have to make your measurements rather indirectly. After all, it's quite subtle and very clever to measure the distance to the moon by eclipsing it. A much more direct method would be to take a tape measure there. Well, of course, that's not possible at all. But we can get a bit more direct by sending something to the moon at a known speed and seeing how long it takes to go there and come back again. Now, I'm not thinking of the astronauts. Their speed's nowhere near constant enough. I'm thinking about a pulse of light. And with the development of the laser in 1960, that's precisely what we do. Now, this is a laser. There's nothing magic about laser light. It's just that it has some rather unusual properties. And the property which is important in this application is that the beam which comes out of the end of the laser tube is very narrow and parallel. Now, I can show you that. If I switch the laser on, you can see that the spot on my hand is only a millimetre or so in diameter. And if I let the beam fall onto the wall, which is a good 4 metres away, the spot still only looks about a millimetre or so. If I move down the wall, the spot's getting further and further away from me. That must be about 10, 15, 20, right down at the end of the building, good 40 metres away. You can still see that very small spot. And way over on that distant building there, 70 or 80 metres away, you can still see it. And I can't quite get it up to the moon, but you get the general idea. The thing is that by the time this spot reaches the moon, it's still only a few miles or so in diameter. However, there are just one or two slight differences between this laser and the laser they do actually use for so-called laser lunar ranging. First of all, this is low power. They need high power to do lunar ranging. But perhaps more importantly, this laser's on all the time. It's a continuous laser. Whereas the laser they use for ranging is a pulse laser. They chop the light on and off. So if you note the time that the pulse of light leaves the laser, gets to the moon, reflected back by the moon, and note the time it gets back again, you know the transit time, therefore. You know the velocity of light, so you can calculate the distance to the moon. And what's more, with the rather fancy cat's eye that the first astronauts put on the moon, we can now measure the distance between any point on the Earth and the moon at any given time to within about a metre or so. So, you see, the technology is improved, but the basic principles are still the same. And personally, I have to admit for a rather sneaking admiration for the way the Greeks went about it. Anyway, if some of you are still disillusioned, not to worry, we're moving on next week. Next week, we're up to the Renaissance and Newton.